Hi, welcome back to CS395. This is Nihal speaking, and this is our final lecture. In this lecture, we are going to be talking about how you can patch binaries and how you can hook functions into those binaries. So you're probably wondering, what is patching? Patching is essentially the act of changing a binary so that it does something that's better for us. So this means that we're going to open up the binary file itself before it's even been loaded into RAM or into memory, and before it's been executed. And we're just going to modify the file so that it does something that's good for us. So this means that we're going to look at the hexadecimal bytes, and maybe we change the value of a variable, or we change a assembly instruction, or we just do something that makes the binary act differently so that it's advantageous for us. Note that since we are writing into the executable itself, you need to have write permissions in order to patch a binary. So if you're trying to, attack some kind of remote server, chances are you can't use this technique because you need to have write permissions on that binary file. And if you're trying to attack like a remote server, you probably won't have those write permissions. So there are limited circumstances where you can use this technique, but even so, it is an incredibly powerful technique that can be used whenever you're running a binary on your own system that you own. One thing to keep in mind is that you're not allowed to patch any binaries or hook functions for your final project unless the program specifically states that you are allowed to do so. Also, whenever you use these techniques, you might accidentally corrupt the file itself. So make sure that you create a backup of the binary file that you're going to be patching before you accidentally corrupt it. So you're probably wondering, okay, if I only have if I can only use this when I have write permissions, when is this technique actually useful? So in most scenarios, again, you're trying to exploit some remote target, so patching won't be very useful. But there are a lot of instances where this is useful for a real world attack. So for example, let's say you go online, you download Microsoft Word or WinRAR or one of those programs that require some kind of license key in order to work. And let's say that the license key itself is hard-coded into the program. What you could do is you could directly go into that file and just directly modify the license key itself so that it works when you type in some different license key. And this is how you have like cracked software or pirated software being created. Keep in mind, this is very much illegal, so please don't actually do this in real life. This is just a theoretical way of how this technique could be used in real life. You could also do something like add your own functions to the binary and have those functions get executed instead of the original functions. So this technique is known as hooking, and it basically involves overriding the function pointers with your own function pointers so that you would change the function that gets called when that function pointer is executed. So this way you can also modify the program's behavior. And in real life, hooking is actually used a lot so that you can intercept data and like understand how it's being used. So another example would be if you were dealing with a program that called a function that checked whether the license key was valid, and what you could do is you could take that function, you could hook your own function and have that executed instead of the original function, and maybe your hooked function could just always return true, so that whenever that function is called, whenever it tries to check your license key, it just constantly returns true. And we're going to be going over an example just like that in a few minutes. But first, we are going to be going over the points program that I created. So let me just open it up. So if I just execute this program, you'll see that it says you have 0 points and you don't have enough points to win. Before I start, just remember that you need to be creating a backup before you begin. So just make a backup real quick, just like that, so that in case we accidentally damage the binary during this process or something like that, we have that backup that we could just keep on using. So the next thing we're going to do is we're going to open up this points program in Ghidra, and I'm going to show you what sort of logic is being used inside of the program. So just give Ghidra a moment to open. We're going to be opening points. Okay. Just give it a moment. Yes, for analyzing it. So we're going to start by looking into the main function, and this is really all we need to look through in Ghidra, because this tells us all the information that we need to know. So you can see that there's this printf statement that says you have %d points, and then points is just this this global variable that I created when I programmed this file. So points is initialized to 0, so that's why when we first execute this program, it's going to say you have 0 points. Then there's this if statement here, and it says if points is less than 100, it's going to print out you don't have enough points to win. So because points is initialized to 0, this is going to be what gets printed out. But if points is greater than or equal to 0 or 100, then what's going to happen is this else statement gets executed, and it says, congrats, you get a shell, and then it gives us a shell. So our goal here is to be able to execute this program and get a shell when we execute the program. So the way that we're going to do this is by patching the binary so that we change the value of this points variable to be 100. And that way, when this if statement gets executed, we this else statement will be executed instead of this this if statement, and it'll give us a shell. So the first thing I want to do is I want to go ahead and look at the assembly for this file. So over here in the assembly, if we take a look at this line right here, you can see that there's a move instruction happening right here. So we're moving some value into EAX. The very next line, we see that EAX is being compared with X63, which is 99 in decimal. So we're comparing the value inside of EAX with 99. So we know that this means that EAX probably contains the value of points. And if we look at the line above, this is probably the line where it's moving the value of the number of points that we have into EAX so that it could be doing this comparison on the very next line. Right after that, we have a jump if less than. So if it's less than 90, if it's less than 100, I mean, then it's going to jump to this line right here. So that is this line right here. And when it jumps to this line, it's just going to print something out and immediately return after that. If this jump is not taken, then you can see that there's a call to put. So it's going to print something out, and there's going to also be a call to system. So what we want is we want EAX over here to be greater than a hex 63. So like hex 64 would be good. And that way, when this jump happens, it's not going to jump over the code that calls system. It's just going to keep on going. It's going to ignore this jump and give us our shell. So the way that we're going to do this is on this line right here, we're going to specifically patch this line of code right here so that instead of having move EAX and then the points value, we're just going to move EAX then hex 64. So we're going to change this instruction right here. So on the left, you can see this information right here is very important. This right here is the offset inside of the file where this assembly instruction is located. So this corresponds to the address where the file has that address inside of has that instruction inside of the file. This is sort of like the offset from 0. And this right here are the hexadecimal bytes that correspond to this assembly right here. So what we're really modifying is we're modifying these hexadecimal bytes so that instead of having it move this points value into EAX, we're going to have it move hex 64 in there instead. And that way we can get our system shell prompt to execute. So the first thing we have to do is we have to figure out, in order to change these bytes, what we're going to be changing these bytes into. And this is pretty easy. We could just create like a real quick test file right here. And we'll just have moved EAX hex 64 in there. And that's it. We'll just assemble that real quick and then do an object dump on it. So in this object dump, you can see we have a move hex 64 into EAX instruction right here. So it's going to set EAX equal to 100. That's, yes, hex 64 is 100 in decimal. And the bytes that correspond to this assembly instruction are written right here. So we have hex B8, hex 64, and then 3 null bytes right after that. When we go back over here and we look at the line that we're trying to patch, notice that it has 6 bytes right here. So 1, 2, 3, 4, 5, 6. So this is 6 bytes long. This instruction is 6 bytes long. But when we look over here, we only have 5 bytes here. So this is going to cause sort of like a misalignment where you have 1 extra null byte at the very end here when we patch this instruction starting at this address. And we don't want that misalignment to occur. We want exactly 6 bytes to be happening inside of the file. Or sorry, we want to patch 6 bytes into the file. And we need it to be exactly 6 bytes because if it's not exactly that amount, it might misalign the file and it might corrupt something. So that's why we need like an extra byte here. And so this is, again, pretty easy to do. You could just add like a NOP at the very end. And that will make it 6 bytes long instead of 5 bytes long. So we're just adding a hex 90 at the very end of this so that we can patch this instruction and patch all 6 bytes. So to do the patching itself, we just have to use Python. So I'm just going to open up Python real quick here, and we're going to say with open, and then the name of the file is points. So we're just going to open up that file, and we are going to be opening it up in the reading and write mode. So that's what the R plus means, and the B means open it in binary mode. And we're just going to name that file F. So when we open this file, we need to figure out what data we're going to be writing into this file. So I'm just going to say data equals, and we'll just make like a byte array here. And this byte array is just going to be these bytes right here. So hex B8, hex 64, hex 00, 90. Right, so it's 6 bytes long, so it's going to patch the entire, all of the 6 bytes, and it's going to patch that entire instruction and replace it with this instruction right here and a NOP right after that. Next, we're going to do f.seek. So f.seek, what this will do is it will change the where our cursor is, and we want our cursor to be right here. So we're going to immediately start writing this many bytes into the file because this is the instruction that we want to patch. Make sure that you indicate that it's hex. And then we just write that data. And that is it. That is all we have to do to patch the file. So if I go back here and I just open up the file again using object dump, if you look at it now, this address, the assembly instruction at this address has changed. So now we see that there's we're moving 100 into EAX, and there's a NOP that happens right after that. Then we compare. Because EAX is currently equal to 100, this jump will not happen, and we will have our call to system be executed. So just to prove it to you all that this is in fact working. This patch does work. I'm going to go ahead and execute the program. And as you can see right here, we do get a shell, and the shell does allow us to type in commands and whatever. In case you're wondering why it says we have 0 points, even though we modified it so that we have 100 points, if we scroll back up to the main function right here, you can see that even though we modified the value of EAX over here, we didn't modify it up here. So up here, it's still using the original value of whatever points was, which was 0, and it's still moving 0 into EAX, which is why that is what gets printed out over here when this printf statement gets called. So if we wanted 100 to get printed out instead of this value right here, we could also patch the instruction at this line of code. And this line of code right here is nearly the exact same line of code that was down here. So the patch for it is going to be pretty much the exact same. All we're going to do is we're going to be using this offset instead of the other offset that we used, which was 117D. So we just have to go into Python. And again, it's the exact same thing that we're doing here. We're opening up the file in reading and writing mode. Then we put in our data. Which is going to be the same thing as what we did last time. And we use f.seek, and this is where it's different. We have to use this address right here instead of the other address that we used earlier, because this address right here is where it's actually moving the points value into EAX so that it can be used for printf later down here. So we're going to do that, and then we're just going to write it. So we write that data into the file. Now when we open it up in an object dump again, if we take a look at the main function again, we can see that we've overridden this line right here as well. So when this printf gets called, and let me just show you right now, when this printf gets called, it's going to use 100 instead of 0. So that is how you patch a binary. You could just easily do it from within Python, just using the built-in Python tools to write data into a file. And all we're doing right here is we're just modifying the assembly instructions inside of the file so that it does something different than what it was supposed to be doing. So this was a very basic example, but if you could imagine this being like a some kind of software that you wanted to crack or that you wanted to use, but maybe it involved like a license key or something, this is how you would get around that sort of software.